thank Molly and Ming and Abbas for inviting me to present this conference. I think this is our favorite conference of the year. So we're going to talk about rock volatiles of cuttings from the Woodford Shale, and mostly we're really going to emphasize reservoir quality and oil versus water wetness, and how we can see these through the cuttings analysis. So this is a unique service that's patented technology invented at AHS, and it's available through Baker Hughes for AHS. What we're trying to do is to map present day oil, gas, formation, water, and reservoir quality, and whatever other properties we can analyze out of the cuttings. We can evaluate old wells and new wells, ducts, whatever. And it works even in wells where logs are challenged. We've done a few wells this year where people had to evacuate because of COVID, so there were no logs taken, and we were really critical in evaluating those wells. Low visibility pays or tight wells, or high pressure, high temperature wells, coiled tubing, etc. So what can cuttings tell us? This is what let me get my laser pointer here. Here's a typical sample of a piece of cuttings. It's less than 1 millimeter in diameter, so it's been through the mill, ground up very small, and then transported a couple miles, washed and dried and stored in a warehouse or something someplace. And sometimes we get cuttings that look like these. These are fake rocks or pseudo rocks. So one side of the cutting looks flat and almost polished. The other side has ridges and valleys. This is the mirror image of the cutter on the drill bit, and this is the side that was rubbing against the formation during drilling. These are made up of thousands of these little pieces of sub-millimeter cuttings to make these fake rocks. We get good information out of both kinds of rocks. This is what our samples look like. So here's some cuttings. Here's one of our sample tubes, about 1 inch in length and 1/4 inch in diameter. It gets filled completely with cuttings. It goes into this brass tube here with a little cotton ball on top of it to keep dust out of the machine. We do both sealed at well and lab loaded cuttings, so we'll talk about both today. Can be water-based mud, oil-based mud, or air drilled. PDC bit or rock bit, cores, new or old, and even 70-year-old cuttings we've been working on up in Alaska. Here's our process. So we load a sample of cuttings. It gets put into a carousel we've modified this auto sampler. It's got a piston here that squeezes the samples at about 2 tons of force. A needle comes down here and goes through this black nitrile cap on the top of the sample. Then some valves are opened, and we drop the pressure inside the tube from about 1 atmosphere down to about 20 millibars, or 1/50th of an atmosphere, in a static vacuum chamber. So it's like opening it to a bottle, nothing's being pumped. And inside there are liquid nitrogen traps. So a liquid nitrogen trap, then we hold the sample in communication with the liquid nitrogen trap for about 7.5 minutes, and we allow all the oil and gas and water and CO2 and sulfur gases and other things that are in the rock that'll volatilize at 20 millibars. We allow them to freeze on to the liquid nitrogen trap for 7.5 minutes. At that time, we close the sample to the liquid nitrogen trap, and we have all these frozen volatiles on the liquid nitrogen trap. We pull a hard vacuum on that, and then we open it to a mass spec, and we let the liquid nitrogen trap warm. And as it warms, different compounds will come off according to their melting or boiling points. And then we analyze this. We get data that pretty much looks like GCMS data. We get compound separation according to their melting points, and we get the mass spectra of those different compounds. A nice thing about this technique is that it's non-selective. So with the GCMS, of course, the column will select the type of compounds that you're analyzing, and with the liquid nitrogen trap, if it freezes, it gets analyzed. It's also very sensitive, so we have a few orders of magnitude better sensitivity than you would with a GCMS. We generate two types of logs. So one is a hydrocarbon log that looks like this. These are two wells in Pennsylvania, both in the Marcellus, a dry gas well, and a liquids rich well that'll produce quite a bit of oil actually from West Virginia. This well just produces methane, but in the shale itself, we see out to sea 5 hydrocarbons trapped in the shale, even though they don't get produced. And so we have our C1 to C8 paraffins here, C6 to C8 naphthenes, C6 to C8 aromatics. We analyze out to C10. We didn't plot it all up because it gets pretty crowded. So this is what we normally give for our hydrocarbon log. Up here, this track, if it's a horizontal well, we're predicting how much oil we believe a lateral would produce going through these strata. And we have our property log. So property log covers a lot of territory. These 3 red curves tell us how much gas we have and what its composition is. These 4 green curves tell us how much oil we have and what its composition is in terms of the main families, aromatics, paraffins, and naphthenes. This is a mechanical strength measurement. We squeeze those brass tubes, and then we measure how thick they are after they get squeezed. We have a permeability index. This one that's plotted here is based on how much hexanes are in the sample. So back to the analysis, we analyze the sample at 20 millibars, and after we're done extracting and analyzing 20 millibars, we take a second aliquot, we call that aliquot 2 at 2 millibars, and then we analyze that, and we see how much oil and gas we get at 20 millibars and how much oil and gas we get at 2 millibars, and we compare that and try to say something about permeability from that data. So instead of pushing helium or mercury into a core plug, we're actually pulling oil and gas out and trying to use that data to say something about permeability. We see organic acids, which are often telling us something about biodegradation. Below 80 degrees C, these formed by microbes chewing on oil, mostly at oil water contacts. We actually go talk about this quite a bit in some other talks here, but this is our water analysis. We're actually, after trying to crack this nut for most of my career, able to now see quantitatively formation water in cuttings and map up pay zones and wettability using that. This is toluene to benzene ratio, tells us about migration. Toluene's a little bit bigger than benzene, so if we have a migration pathway, we tend to leave more toluene behind than benzene. And these 4 tracks tell us about the nature of the oil, its composition, and they also tell us about the reservoir. So we have a heavies to gasoline fraction, a gas oil ratio, paraffins to naphthenes, and aromatics to naphthenes. So these are the curves that make up the property log. Today we're going to be focusing on these curves quite a bit, the oil curves, and also on these mechanical strength curves. So for each analysis, we have 2 extractions, one at 20 millibars and one 2 millibars. We have 2 types of samples that we work on, washed and dried samples that we generally get in little cuttings envelopes, that we load them in the lab. We have to crush those at the start of the extraction because usually all the juicy stuff on the outside of the cuttings has disappeared, and so we need to open up fresh surfaces. And we have sealed at the well cuttings that we actually catch the sample before it hits the possum belly. So as it comes out of the flow line and going into the possum belly, we catch it in a little kitchen strainer, rinse it off, float it into our tubes, and seal it right there within a minute of it coming out of the flow line. These we don't crush before we extract. We crush them after we extract them, but we don't crush before we extract them. They're wet and tend to have be very ductile because they're wet, and if we crush them before we extract, the tubes get so small that we don't get the oil and gas out. So lab loaded, we crush before we extract, seal at the well, we crush after we extract. So the title is Rock Volatile Analysis, Woodford, Shale Cuttings, etc. But really we're going to emphasize reservoir quality and oil versus water wetness, and especially look at the role of faults in both of these. This is some of our data. This is a Woodford lateral drilled in the Arkoma Basin. This is the geosteering up here. We have lots of faults. You can see pretty convoluted geosteering to accommodate all these faults. And here's our data. These are sealed at the well samples, and you can see there's a lot of heterogeneity in the data. We have a big slug of liquid-rich cuttings out here, and then we don't see that in most of it. We see some liquids here. We don't see any over here. We don't see any over here. We see a bunch of formic acid right here. Don't really see any over here. We see very high heavies to gasoline ratios here. We don't see that here. So there's a lot of changes that happen. Part of what we're going to try to do in this talk is like, why is that? And this is the same well. These are the lab loaded cuttings. We can see in the lab loaded cuttings, we're seeing a fair amount of oil over a larger distance. In the other slide, we were just here with the oil. But here we have oil from here to here. Again, there seems to be some association with the faulting. And towards the heel, we see very little oil in the cuttings. When we put that together, it looks something like that. Here's where we're seeing oil in the sealed at well cuttings, and here's where we're seeing oil in the lab loaded cuttings. And again, we're going to come back to this well. But our mission today is to understand what is going on here, why in both of these sets of data, the lab loaded and the sealed well, why do we see oil in parts of the reservoir and not in others in the cuttings, and why is there a difference between the lab loaded analyses versus the sealed at well analyses? So that'll be what we'll be working on. We'll be working up to where we can interpret what's happening here. First, we're going to look at some data from lab loaded cuttings, and what can we learn from those? Mostly something about reservoir quality and mechanical strength and the effects of faults on both of these. And we're not going to see this today, but on lab loaded cuttings from our water analysis, we can tell something about oil versus water wetness, but these samples were analyzed before we perfected that technique. This is for the wells we're going to look at. This was the best well drilled. It's going to be on the same scale. This is what a great well looks like. Here's the oil curves. You basically don't see any oil in this reservoir. This is because good reservoir rocks lose its oil and gas between the drill bit and the way to the surface. So this is what the best well in this set of wells looks like. This is a poor performing well. You can see there's lots of oil and gas in the cuttings here. These rocks are tight. When they come to the surface, they maintain their oil and gas in the cuttings because they are tight and they're poor reservoir rocks. So the amount of oil and gas in cuttings isn't really a good indication of producibility. Really, the better reservoir rocks here or over here. And again, here's the best well, and then here's another good well where we're not seeing very much oil in the cuttings, and another one where we're not seeing very much oil in the cuttings, and then back to this one that is a poor performing well where we do see a lot of oil in the cuttings. And so what's going on here? We have two big faults here towards the toe. And that's associated with where we have all this oil in the cuttings. When we can divide this well up into several compartments, here we have most oil. We also see higher formic and acetic acid. One important thing is we see on this low mechanical strength on our measurement. Now, this is some kind of microfabric destruction. It's different than other mechanical strength measurements. We've just been working up in the North Slope of Alaska. We can tell the permafrost sediments from this type of mechanical microfabric destruction, and I think people have been studying this up there for years with the first technique that actually picks out a mechanical strength difference in the permafrost sediments. So that's what this is. These faults are causing lots of microfractures in these rocks here, and we're seeing that when we squeeze the samples. Right next to that, we have a zone of high mechanical strength. Now this is higher than our normal mechanical strength, and we typically are seeing this around faults. Right at the faults, we'll see low mechanical strength and adjacent to it higher, and then back to normal Woodford mechanical strengths. And so this looks like microfabric destruction. Looks like over here we're getting some kind of cementation, probably from fault-associated fluids that are invading into the Woodford here. And all this section, we're having high oil in the cuttings, which is telling us that these rocks are tight, and goes with the fact that this is a very poor performing well. Again, this is what a good performing well looks like. Not seeing very much oil in the cuttings. And these two wells are actually drilled from the same pad. Here's the good performing well, it went this way to the south. The bad performing well drilled this way to the north and into these faults. This is where the pad is. We put them together to make one 4-mile lateral. You can see here's the faults, here's the tight rock that's not producing very well. Low mechanical strength, high mechanical strength, and normal Woodford type mechanical strength for most of the well. And this well, which is a great producer, then showing very little in the way of oil in the cuttings here. So that's all this tells all that story here, the faults and the low mechanical strength, high mechanical strength, normal mechanical strength, high oil in the cuttings, low oil in the cuttings. So what can we say from lab loaded Woodford? Well, we can say where we have good reservoir quality, which has low oil in the cuttings, versus bad reservoir quality, which has high oil in the cuttings. We can see something about mechanical strength. Low mechanical strength right around where the faults are. The faults seem to affect both reservoir quality and mechanical strength. And we're going to talk about oil versus water wetness, but not with our water data today. So in general, from the lab loaded, these wells and other wells, simpler is better. Faults are not your friends in the Woodford in general. Sometimes they don't hurt you too much, but a lot of times they tend to be you tend to get poor reservoir quality, mechanical disruption, and cementation. So now we want to look back to the question of the sealed at the well versus the lab loaded. So we extract at 20 millibars and 2 millibars. Lab loaded, we crush at the beginning of extraction. Sealed at well, we extract without crushing. And this is the guide that we want to interpret at the end of this talk. First, we're going to talk a little bit about some other wells. Here's some Northwest Stack wells. These are same well, lab loaded samples, sealed at well samples. What you can see is we're seeing more oil in the sealed at well samples than we are in the lab loaded samples. This is a good reservoir here. You see more oil in the cuttings here. And what this is telling us, so our data, we interpret our data indicate this is where the pay zone is in this lateral. We go through a big fault here, and the rest of the well is pretty much out of the pay zone. What the having quite a bit of oil in the sealed and not very much in the lab loaded is what we expect from water wetting rocks. So water wetting rocks will tend to lose their oil, and oil wetting rocks like to hold on to their oil. So in the water wetting rocks at the sealed at the well samples, we see more oil coming out of the sealed at the well samples than we do out of the lab loaded samples. And here's another, this is a vertical well, vertical Woodford well that goes into a lateral down here. So this part's vertical, this is the lateral. This is the, here we got the, get my name thing out of there. Here we got the sealed at the well samples. Here we have the lab loaded samples. You can see we have more oil coming out of the lab loaded samples than we do out of the sealed at well samples. And let's see. And this well is what we would call oil wetting. So here, the sealed at the well samples are not giving up their oil. We have to actually come in here and crush the lab loaded samples to get the oil to release. So this greater amount of effort that we need to get the oil out of the samples are telling us that these are oil wetting. So oil and cuttings from oil wetting reservoirs want to stay in the cuttings. Here's another lateral in the Woodford. You can see sealed at the well, we have low oil. In the lab loaded, we have high oil. This is telling us that this is an oil wetting lateral. Here we have a vertical well that drilled last year, went from the Caney down into the Woodford. Here's we have the sealed at the well. Here we have the lab loaded. You can see immediately we have a lot of oil up here in the Caney section, the upper Sycamore in the lab loaded, and then also down here in the Woodford, we're seeing more oil. This is actually scaled on total oil from 0 to 30,000 parts per million, or 3%. Over here, it's only scaled to 0 to 10,000 parts per million, or 1%. So if we scaled this at the same, it would even look like less oil over here. So when we plot this up, then we say that these parts of the well are oil wetting, and this part here, the Sycamore, looks to be more water wetting than oil wetting. So some wells are both oil wetting and water wetting. We come back to this well that we keep on talking about, and we see the sealed at the well samples and the lab loaded samples. We put them together. What we end up with is this. So these samples give off more oil in the sealed at well analyses, and then we're seeing less oil in the sealed at well here. We're seeing lots of oil in this part in the lab loaded. This is telling us this is bad reservoir. This is bad reservoir that's water wetting here. We also get the higher amounts of organic acids. We get this lower heavies to gasoline range, which is more indicative of the actual oil quality than we're seeing over here and here. But this is what's happening here, that this part of the well near these faults has become water wetting. This is probably not some kind of change in the organic matter, but probably also related to a bunch of micro fractures and stuff that are now in the Woodford. Then those fractures are probably water wetting, and that's what's causing this oil to leave these cuttings more easily than the oil wetting cuttings. This is another well that's showing this kind of behavior with parts of the lateral in the sealed samples are showing oil and parts of it are not showing oil. But here we have good reservoir throughout on the lab loaded samples. So we have broken this down into most of this Woodford looks like it's water wetting, and then this part up here looks like it's oil wetting. All the reservoir looks to be a very good reservoir though. So basically, kind of wrapping up, simpler unfaulted wells tend to be better. Here, we got a lot of faults, but it's working out pretty good. But here we have all these faults. We have lots of tight rocks and stuff. We have disruption, mechanical disruption of the sediments and tight rocks. And this well, not going to be great around here, probably better out here. This well also got a lot of water wetting quality to it, and it's associated with these faults, probably disrupting the microfabric of the Woodford. So simpler is better. Woodford near faults tend to have poor reservoir quality caused by mechanical disruption and cementation. So probably ran through this a little too quick, but I wanted to show you that in these wells where we have both sealed at the well versus lab loaded cuttings analysis, we get a feeling that parts of the reservoir are more water wetting and parts of them are more oil wetting. The more water wetting parts of the reservoir tend to be associated with the faults and appear to be associated with some kind of structural damage to the rock. And so we have these probably microfabric sort of micro fractures that are added to the reservoir volume, which are water wet and are allowing the oil to come out of the cuttings more easily as when we analyze them as the sealed at well cuttings. Again, just simpler unfaulted Woodford is better. You know, sometimes the faults don't hurt you too much, but these big giant faults are not very friendly. Woodford near these large faults tend to be tight and often change from oil wetting to water wetting. And I think that's where I'd like to leave it. So again, I'd like to thank the organizers for inviting us, and you know, I'd like to thank our partners at Baker Hughes for working with us on this also. And my thanks go to my AHS staff, Christopher Smith, Patrick Gordon, and Timothy Smith, without whom this work couldn't be done. It's a great team. I sincerely think that there's no other group of 4 people in the world that could be doing what we're doing at the moment. So thanks, everybody.